Recording. Okay, 11.3, 11.5, 11.7, and 8, electric potential difference, current and resistance. The learning goal is define electrical energy, how it's measured, and how it's transferred. Calculate potential difference for a given load. A load is like a resistance or light bulb. Determine how current and resistance impact a load. Define Ohm's law to relate current, resistance, and potential difference. Okay, now first things we want to see what is the electric charge Q. So you know the when we have a circuit, you have a wires, right? This is the wire, this is the resistance, this is a battery. Battery is positive to negative. You know the electron travel from negative port to the positive one. Conventionally, we do the positive to negative because you want to say that the positive charges is moving. Conventionally, why we do that? Because it's easier to work with positive number easily. This is conventionally. But here, a form of charge, either positive or negative, that exert an electric force. Um, what is responsible for causing electric charge on a substance? Okay, the electron is moving, okay, actually moving from negative side to the positive, right? This is the direction of the electron moving, and here is the direction of the positive charge is moving, right? But conventionally, we always say in a circuit that the positive charge is moving. What caused this charge to move? Potential difference. Do you remember that when I was teaching you uh, mm, gravitational potential, if you hold something uh, and it has some distance to the surface of the earth, then you could say that this has a potential energy and the potential energy is mgh. And when you release this, is go back, this potential energy change into the kinetic energy, and if you dig around. They ask you, how do you know when you hold this, it possesses potential energy? You would say, I let it go, is potential energy turn into kinetic energy. And that's how we know the energy is stored in this, right? The same thing happening when you have when you have a battery, the electron move through the sticker. And how does it move? Because it possesses potential energy, right? There's potential difference between these two, and it forcing the charge to move from a place to another place. From higher potential, it moved to the lower potential. So positive part has a higher potential and the negative is a lower potential. That's why the positive charge is moving like that, right? The same concept from the higher potential, gravitational potential, to lower gravitational potential. Same concept lie here. Everything in nature going toward lower potential energy. Either is in a, can talk about it in the electrical circuit, or we can talk about it gravitational or any other concepts related to the potential. You can apply this concept. So very important. Um, so electric charge is therefore a measure of how many electrons we have in a substance. Um, so 1 coulomb. So we measure the charges by coulomb. If I say what is the 1 coulomb and is the measure of the charge, is like a meter is a measurement of the length. Coulomb is a unit for charge. 1 coulomb is how many electrons? Is 6.24 10 power 18 electrons. Okay, or 6.24 quintillion, right? That's a huge number. Electrical energy, again, I did talk to you about the energy, but let's just see what it's saying. defined as electric charge that can do work. This means it can convert its energy to mm, another usable form like light, sound, heat, etc. And I'm just gonna put the circuit here. Let's say you have a light bulb here, right? When the positive charge is moving from positive to the negative. So when it hit the light bulbs, it's turn the energy of this charge will be transferred into the light and heat, right? Because when you touch it, you will feel the heat, right? So you can use electricity to turn on the light. That's why the this energy, electrical energy of the charge, will turn into light and heat. The light is a useful, and the heat is kind of because you have a resistance here. It turns the heat. You're not using the heat, but it's there. This is measure of the unit. Okay, and you know the energy of the electrons, we call it joule. The energy, the unit of energy is joule. I did talk to you about the potential difference earlier. Now we put that in equation form. The difference in electrical potential energy per unit charge measure at two different points. Okay, I'm gonna put the circuit again. Let's just put the light bulb. And here is that. If you talk about two different points on this circle, like here and here, and you put the voltmeter, you can measure the potential difference between the 2 point on a circuit, right? Uh, so it represents the amount of energy per charge. Higher voltage, it means your electron can is more energetic, right? So an equation is coming with that equation. So its voltage is energy per unit charge, energy that each charge possess. So joule per coulomb is voltage, or is the volts. These are the units, joule per coulomb, or you can say the volts. But this is an example. What is the potential difference running through a light bulb that gets 25 joule of energy? So energy is 25 joule from a 3 coulomb charge. Okay, so Q is 3 coulomb. So you know potential is 25 divide, okay, let me just put the equation first. Okay, get that. It's energy per coulomb. Energy per charge is 25 divided by 3 is joule per coulomb. I'm not putting in that calculator, just that. Example 2, how much energy does this 4.5 coulomb charge have? So this is Q, it's 4.5 coulomb if the load receives 5 volts. So voltage is 5 volt. Again, voltage is equal to E, energy over Q. I'm solving for E. So E is V multiplied by Q. So I know V is 5 and Q is 4.5. It's 22.5 joule. That's the energy, right? So this is joule per coulomb multiplied by coulomb. So coulomb cancel, and you're left with joules. Very simple. You have seen power. Again, you have a same situation here when you are talking about electrical charges. You're is dealing with energy, change in energy, right? Change in energy is work. So power, we did see that it was work over time. The work was in joule and time in second, joule per second. It was watt, right? The unit of the joule per second is the same as watt. You had that in the previous unit. Um, so we know that the work is equal to the change in energy, right? Change in kinetic energy or potential energy. Here, we can replace work by energy here, electrical energy, the energy that each charge possesses. Because when the charge located on the battery do not have any energy, right? Once these you connecting the wires, you connecting the wires, this charge getting energy means from zero energy they get some energy. So the change in energy, kind of the uh, final energy minus initial energy. Initial energy was zero, final energy they have some, so just replace that by energy. Again, it's going to be joule per second. And let's just look at that. There are some appliances and their powers. There is a blender, is 500 joule per second. I believe it's going to be joule per second, right? Is it? They didn't say in a unit, but assume that it's joule per second or watts. Oh yeah, watts. Can opener, more powerful. Like a blender needs a lot of power, right? Like coffee machines, you can just look at the different numbers that you see that. These are the bulbs, different type of the bulbs, and all having different powers. You can compare them. Now, this is a question. Calculate the power of a kettle that is supplied 4,500 joule of energy in 45 seconds. So again, power is energy over time. The energy is oops, not writing, 4500. Let me just make it nicer. 4500 joule. The time is 45 seconds, so it's going to be 100 joule per second, or you can say this is 100 watts. So that's the power. Now, this is the definition of current. Current is the amount of charge passing a point in a given second. So if you think about a wire here, the amount of the charge passing through the wire, the Q, right? Amount of the charge passing through this wire um, over the interval of the time will give you the current. More charges passing, um, it means it's the current. You have a high current. So time is a time in second, Q is in coulombs, I is a current in ampere. So the unit for current is ampere.
Mrs. Let me submit the quiz.
Okay, thank you. I will check that in a minute. Just finish this one. Danger of electricity. There are some cautions that you need to take into account if these devices that you're using high voltage, high powers. Um, so how much current runs through a typical outlet? What safety measure we do? So if the current is 1, if it's really fatal, it's cause severe burns and death, breathing stop. So from zero point 0.1 above is death, right? And from 0.01 to 0.1 is not bad. It's breathing difficulties, severe shock, muscle pain, and so on. And from 0 to 0.1 is a mild sensation and not that bad, right? It's just making that precautions. You're using different outlets. especially in factories. They have a huge, maybe voltages or currents passing through their devices. It's more dangerous. Um, so 1,000 milliamperes or 1 ampere, it will light 100-watt bulb. 900 severe burns, 300 breathing stops, and just again, this is kind of what we did here, but sorry. Okay, let's just do this one. What is the current if the 5 coulomb charge passes the point 3.5 second? So again, I is equal to Q over time. What is the current? I'm looking for I, so Q is 5 coulomb, time is 3.5 second. You just divide these two and it's coulomb per second. I'm not doing that numbers, just quickly, so you see. How long does it take for a 12 coulomb charge to pass a given point if the ampere measure is 2 amp? Okay, we're looking for time. Is that how long? For 12 coulomb charge, so we have Q is 12 coulomb. The ampere measure is 2 amp, so I is 2 amp, right? So knowing the I is Q over time, and you're looking for time, so it means it's going to be Q over current. Q is 12 coulomb, I is 2 amp. Oops. If you divide that, I would give you a second, right? Of course. 12 over 6 second. Now here is another power equation that you use. Again, what is the power? The amount of energy supplied an object in a given period of time. So we did see that the power was energy over time, right? We did have that before. Measured in what? This can be found by multiplying the potential difference V and the current I. Uh, just remind you that voltage was energy per Q. Remember that equation? Also, I was Q over time. If you multiply these two, V multiplied by I, you have E over Q multiplied by Q over T. What do you get? Q and Q cancel, energy over time. What was energy over time? That was power, right? So then I can say the power is voltage multiplied by current. So that's another equation that useful to use. Okay, this is very handy. What is, okay, this example, what is the power of the device with 3 amp and 14 volt running through it? Power again is, I have amp and also it's going to be IV, right? 3 multiplied by 14, 42. I can say that joule per second, or I can say this is watts, right? Or you know that is amp multiplied by voltage. So any unit acceptable because this is amp and this is the volt, right? Can use any of those units. Okay, so for fun, remember with great power comes great current squared times resistance. I'll never forget this dying ankles at the white. Okay, so what is that? All right, so this is another equation I think is funny, but let me see if this is here. Maybe I prove that for you. Okay. So power again, we said power is equal to voltage multiplied by current. Um, comes great current square. So we know the voltage is equal to Ri. This is something that I didn't talk about that, but I believe you have seen it in Science 10. If you have a circuit, and here is the resistance, then you have battery. Battery provides potential difference. If you just put a voltmeter here, it will give this electron or positive charges the potential difference, and this potential difference pushing these charges to move through the circuits. If you have a light bulb, uh, it will turn on your light bulb. If you have any devices, it'll turn your devices. Any devices has a resistance, right? That's why I put this load resistance here. So it produces a current because the charge is moving, right? So it's I. We have I current. And here is the relationship between this voltage, current, and the resistance here we have. Voltage is equal to resistance multiplied by I. Now, if I replace the V here by Ri, so my power gets to this equation. It's getting R I power 2. See, this is what it's saying. With a great great current square, like I power 2 is a square current, time resistance. But it's kind of make it funny with this picture. Kind of this person is resisting power or something. That was fun. And you know, the unit for resistance is ohm, unit for current is ampere, and here is volt. Voltage is volt. We could do another things here. Again, I'm just writing down power is voltage multiplied by I. I can rearrange this equation and say I I is equal to voltage divided by R, right? So instead of the I put voltage divided by R. So we'll have a V power 2 over R. So this is another handy equation. That would be nice to remember. Okay. These three equations are the same. P is V multiplied by I, or R I power 2, or V power 2 over R. So resistance, now we're talking about the resistance. I just did talk to you about the resistance in a circuit, the ability of material to oppose the flow of electric current measured in ohm. When you have a resistance, it will cause electrons to slow down. So it taking the energy of the electrons. So here is the resistance, the electrons comes, or the positive charge is coming. It will slow it down, and this energy wasted, and sometimes you will see that energy is in form of the heat. Okay. Greater resistance, the warmer the material becomes because the energy of the charge will transfer it into the heat. So for factor of factor resistance, type of the material, cross-sectional area, length, and temperature. I hope that we have those equations. Yeah, we have. I'm just getting there. So type of material, some material like gold and silver, copper, they really have they are a very good conductor and they're low resistance. It's very good to use it and make a wire with, right? So you don't waste energy if you use copper. The gold is very expensive, that's why we don't use it, or silver is very expensive, right? But copper is kind of reasonable for us to use the copper to make wires. So silver resistance is even lower. Why we don't use it? Because it's expensive. So cross-sectional area is another things that affect the resistance. bigger, the larger the face, the less resistance. Okay. This is because there is more area that the electron can move through freely. Why we do not use the massive wires? Because it become very heavy, right? We don't want to also expensive is not convenient to have a very big area cross section. That's why you make it reasonably small, something like that. Okay. Length. Also, it could be dangerous because the cross section is huge. Okay, length. So the length of the wire, the of course the lengthier it is, it has more resistance because the path that the electron is moving through, it's bigger, so it's losing more energy, right? Through a larger path than shorter path. Um, right. As you see, for this one, because it's a long wire, it caused some fire and burning here. This is a fire hazards for long extension cords. Temperature. As you increase the temperature, what happening to the molecules? Molecules go faster. Like just imagine that this is my wire, right? And it's electrons, these molecules, right? You heat it up, they move faster. Just let this go up, down. And when electron coming, it can hardly pass through easily, right? The chance that the electron hit this molecule gonna increase because they are moving very fast and it comes, it's more probable that it hits one of those molecules, losing energy. Losing the electron lose energy means it's producing heat, means the resistance going up. So this turn caused more collision within the wire, increasing the internal resistance. Resistor in circuits. Resistor, device that reduce the flow of electric current. Any devices you put in a, you connected with wires and the electric charge passed through it, so it's kind of a resistance. We have different type of resistor. If you can change the resistors, it's a variable resistor. Uh, so some lights, you can use it as a dimmer or writers. You can change the resistor, right? And just change those brightness of the lights. Now, this is the one that I did talk to you. I don't want to do that because the R resistance is voltage over I. I put that again. This is the resistor. This is the battery, produce current. And here is the voltage. The battery provide the voltage. V is equal to Ri or IR. And you can rearrange it for RR is equal to voltage over I. And you know that's unit for resistance is ohm. There is volt. And for I is current is ampere. Now let's just look at this example. The potential difference measured through a light bulb was find. This is a voltage, 5.5 volt. If the current through the light bulb is 6.5 amp, what is the resistance? So V is equal to Ri. You can say that R is equal to V over I. Voltage is 5.5 divided by 6.5. The unit is ohm. Example 8, what's the potential difference of a stove with a 25 of current? So I is 25 amp. Passing through a resistance, R is 45 ohm. We're looking for potential difference, V. Again, V is equal to Ri or IR. R is 45 multiply by 25. We do this one, and the unit gonna be volts. Here is success created. I can define to calculate the electrical energy and potential difference for a device, define current, resistance, and factors that affect them, calculate current, resistance, and power for a load.